Okay, so this is for any set S. Look at set of all functions from S to R. As we saw earlier, this has a natural ring structure with pointwise addition and pointwise multiplication. Now, we already saw as an example of an ideal, look at set of all. So, take a subset A, take a subset A of S and look at I of A to be set of all f from S to R such that f of A is 0 for every A in A. Okay. This is an ideal of f of S. My question was, can you think of a prime ideal here? Okay. Maximal ideal. Okay. So, I mean, if you have not spent some time thinking about it, I will leave it. We will come back to this example later. Think about it, it's a nice example. If you put some additional structure on this, you can look at a subring of this called. So, again, if you have, you need to have some structure on the set. I look at CAB, my S is the interval AB, closed interval AB. This is set of all continuous functions. Then F, this is then CAB is a subring of FAB. Now, it is interesting to think about ideals of CAB. It is little, I mean, it has little more structure, because AB is, this is a topological space. It has a subspace topology coming from the usual topology of R. So, with that you can talk, you can think more about functions. There are, there will not be functions, not all functions like this appearing here will be here, right. For example, if S is, if you look at in this one, you can define all functions f of 0, f of x equal to 0 if x is rational, and if f of x is 1 if x is irrational. It will be here, but not here, right. So, similarly, this has more structure and hence it is more interesting, and the ideals, in particular the maximal ideals of this are of very particular form. We will come back to that later. So, the question is, suppose you have a ring, commutative ring with identity, okay. Does it have a maximal ideal at all? It can, maybe there is a possibility that I have ideals I1, the only ideals of A are like this, a chain which never stops. There is no ideal which is at, which is at the top of all other ideals, or at least there is nothing between, there is no ideal, proper ideal which contains a lot of ideals, or which is not a proper ideal of any other, sub ideal of any other ideal. How do I make sure that there exists something like that? Okay. So, this is, let us take the collection of all this be set of all ideals. I is a proper ideal of of A. So, let us assume A to be a non-zero ring. Okay. Now, can you see that this is non-empty? Why is it non-empty? The 0 ideal belongs to sigma. So, this says that this is non-empty. This is collection of all ideals. So, this has a natural partial order, the inclusion, right. So, if you want to, so the idea is, see, I am looking for, I am trying to see if I can get a maximal ideal. If I can get a maximal element in this one, naturally we expect that it is a maximal ideal, right. So, the question is, can we have a maximal element in this one? How do we think of when you get a set which is partially ordered set and you are looking for a maximal element, what is the result that comes to your mind? Zorn's lemma, right. So, to apply Zorn's lemma, you need to say that any chain of elements will have a maximal element in sigma. So, let us take a chain in sigma. Let I1 contained in I2 be a chain in sigma. And you want to look for a maximal element in sigma. What should be, can you think of a natural candidate for this? I will have to look, I am looking for an ideal which is proper. Yeah. So, if you look at, in general, if you take I1 and I2, two ideals or collection of ideals, their union need not be an ideal, right. If you take a, if you have a collection I lambda, lambda belongs to some indexing set, this need not imply that union I lambda is an ideal, right. Union of two ideals need not be an ideal. Can you tell me a quick example? Whenever you think of examples, I would expect that you think of Z, right. In Z, if you take 2Z and 3Z, take their union, right, it is not an ideal. Why is it not an ideal? Well, for that you need to prove more things, but it is immediately you can prove that you can say that it does not contain certain elements. 2 is there, 3 is there, but 5 is not there, right. So, that immediately says that it is not an ideal. So, therefore, union need not be an ideal, but if you have an increasing chain of ideals, union, so this is okay, maybe I will use a different notation here because I am using I for this I n from 1 to infinity is an ideal, because this is, since I1 is an increasing chain. And of course, you need to verify that it satisfies all the properties, usual properties of now the question is this a proper ideal? See, we need to, given any chain, I need to find an upper bound of this chain, upper bound for this chain in sigma. For this ideal to be in sigma, we have to show that it is a proper ideal. Why is this a proper ideal? What is meant by this is not a proper ideal? It is equal to the whole ring A. When do you say a union is the whole ring? Yeah, in this ideal is, this is an ideal is whole ring if and only if a unit belongs to it. So ideal In has a unit, it has one element, the element identity is in the union, therefore it is in one of them, but if it is in one of them, if an ideal contains identity, then it is the whole ring. That is a contradiction, right. So, if union In is equal to A, then 1 belongs to the union. That implies 1 belongs to In for some n. That implies In is equal to A, which is a contradiction. Contradiction to the assumption that In is proper. So, therefore, this union belongs to sigma and this is an upper bound for the chain. I1 contained in I2. And so, what we have seen or what we have shown now is that given any chain, increasing chain in or given any chain in sigma, it has an upper bound in sigma. So, therefore, by Zorn's lemma, sigma has a maximal element. This has a maximal element. Okay. Let us say denote that by M, and we expect this to be a maximal ideal, right. Let us see if this is a maximal ideal. What is meant by this is not a maximal ideal? There exists an ideal, let us say J, which is a proper ideal of A and properly containing M, but that directly contradicts the maximality of M in sigma. So, J belongs to M sigma and that will contradict the maximality of M. So, therefore, if M is not a maximal ideal, then there exists a proper ideal J such that M is strictly contained in J. This implies that J belongs to sigma because it is a proper ideal and M is strictly contained in J, and these two together contradicts the maximality of M, contradicts to the conclusion here that M is a maximal element of sigma. So, therefore, M is indeed a maximal ideal. So, what did we prove now? If A is a commutative ring with identity, A is a non-zero commutative ring with identity, then A has a maximal ideal. So, let us so therefore, we proved if A is a non-zero commutative ring with identity, then A has maximal ideal. So, this method of finding maximal element, we will see it a couple of times in this course, not couple of times, I mean more than that. Getting a collection of ideals or modules and then looking for a maximal element in that, okay, using Zorn's lemma. This is something, this is a standard tool in commutative algebra. Okay. So, this is, this has a nice corollary. Suppose I is a proper ideal of A. If I is a proper ideal of A, so what we have shown now is that given any commutative ring with identity, it contains a maximal ideal. Now, I can demand more. I take an ideal I, can we have a maximal ideal containing I? So, there are two ways of doing it. One, that you can repeat the proof. You can consider collection of all proper ideals containing I and then go through the same process. If my collection I modify to be that, the whole thing goes through exactly as it is, there is no difference. That is double work, I mean you are duplicating your work. Much simpler is look at the ring A mod I. If you look at the ring A mod I, this is again a commutative ring with identity, non-zero because I is a proper ideal. Therefore, this has a maximal ideal. Now, you have a natural map from A to A mod I. Using this, you can show that the maximal, the inverse image of the maximal ideal here will be a maximal ideal here containing I. So, therefore, a corollary of this is if A is a commutative ring with identity, and I is a proper ideal of A, then there exists a maximal ideal in A containing I. This corollary has one more nice corollary, actually an observation. If you take any non-unit element, if you start with some element of A which is not a unit element, then there exists a maximal ideal containing this element. Can you see that? Every non-unit is contained in some maximal ideal. Can you see that? Look at the ideal generated by X and apply this corollary, right. So, every non-unit is there in some maximal ideal, or there exists a maximal ideal containing a non-unit. So, if X in A is a non-unit, then there exists a maximal ideal containing X. So, this is apply corollary, the previous corollary with so what we have shown now is that given any non-unit, it is in some maximal ideal. So, now suppose I collect all non-units of a ring, will that form an ideal?
No.
Need not necessarily form an ideal. For example, can you think of a ring where this is not true? That all non-units do not form an ideal? Collect all non-units of that ring, that is not an ideal. Can you think of a ring with this property? Z itself, right? In Z, except 1 and minus 1, you collect all of them, that is not an ideal, right. So, therefore, the collection of all non-units do not form an ideal, but suppose it is true, okay. Suppose the collection of all non-units form an ideal, what kind of ideal will it be? Let I be equal to set of all X in A, X is a non-unit. So, our basic assumption on A is that A is a commutative ring with identity, right. I am collecting all non-units of A. Will it be a proper set, proper subset of A? Yes, because 1 is not there in there. Now, suppose this is I is an ideal. Can you make some more observation about the ideal I? Will it be a maximal ideal? You take any X in I, then by the previous observation there exists a maximal ideal containing this element. But now if you look at the elements of that maximal ideal, all elements in that ideal should be non-units. That means all of them should be here. This is an ideal and maximal ideal is, this is a proper ideal and the maximal ideal is contained in this one, which means they have to be equal, or in other words I is a maximal ideal. So, if collection of all non-units form an ideal, it has to be a maximal ideal. Okay. And okay, I will make one more observation. So, if X belongs to I, then there exists a maximal ideal in A containing X, say M for each y in M, y is a non-unit because it is in a maximal ideal, and that implies that y belongs to I. This implies that M is contained in I, this implies that M is equal to I, and that implies that I is maximal ideal. Now, in this case we proved little more. Can you see? We proved that I is maximal ideal, yes, but we proved little more than that. See, here we happen to take a maximal ideal of A and we proved that it is indeed equal to I. Any maximal ideal is equal to I. That is what we indeed proved, right. You started with some element of I, or in fact I could start with any non-unit of A, then I have a maximal ideal containing that non-unit, and we proved that that maximal ideal is indeed equal to I. Therefore, what we have proved is that there is only one maximal ideal, which is I. Okay. So, this such rings where there is only one maximal ideal is called a local ring. So, therefore, what we proved is the following. Okay, let me make one more observation here, that also I is the only maximal ideal of okay. So, yeah, I will come back to this. So, this is what we have proved now is that if the set of all non-units say I form an ideal, form a proper ideal of form an ideal, we do not really need to say proper because it is naturally proper form an ideal of A, then I is the unique maximal ideal in A. This is what we proved here. That is the only maximal ideal of A. A ring is said to be a local ring if it has only one maximal ideal. Can you think of some examples of local rings? Is Z a local ring? No. Can you make a local ring from Z? Can you construct a local ring from Z? So, in general, if you take basic example, any field, right? If you take any field, it has only two ideals, either 0 or the entire ring. 0 is a maximal ideal there. So, that is the only maximal ideal. But now can you give me an example of a ring which is not a field but a local ring? Again, think of the correspondence between quotient and the ring. From Z, can you construct a ring which is local? Not fields, again, do not tell me Z2, Z3, Z5 and so on. Give me an example of a ring which has only one maximal ideal. So, as a basic example, let us look at Z9. What are the maximal ideals of Z9? So, this is isomorphic to Z mod 9Z. Maximal ideals of this ring would be of the form Pz by 9Z, where P is a divisor of 9. There is only one, which is 3. Ideal generated by 3 in this ring, right? That is the only maximal ideal. So, more generally, Z mod P power nz, where P is a prime, this is an example of a local ring. Okay. Now, we have one more nice characterization of local rings. So, if you take, this is let A be a commutative ring with identity. So, I will just say let A be a ring. This means A is a commutative ring with identity and M be a maximal ideal. If 1 plus x in M is a unit for all x in M, then M is the unique maximal ideal of A. So, M is a maximal ideal So, how do you say that 1 plus x is a unit? How do you say that 1 plus x is a unit in I am sorry, we are assuming that 1 plus x is a unit in M. How do you say that M is the unique maximal ideal? So, suppose I have, let x be, see, how do you say that this is the unique maximal ideal? If I can show that all non-units are here, okay, then we are through. So, if I take a non-unit, if it is not in M, then we get something, right. Let x be a non-unit, okay. This, if x is not in M, then see M is a maximal ideal. Therefore, if I take the ideal generated by M and x, it has to be the entire ring, right. Then M plus x has to be whole of A. or in other words, there exists some u in M and some r in A such that 1 is equal to u plus r x. U is in M, this implies 1 minus u is equal to r x. U is in M, therefore 1 minus u by assumption is a unit, which means r x is a unit, which means x is a unit. That is a contradiction. Therefore, x has to be in M, which means all non-units are in M, which means M is the collection of all non-units, and hence it is a maximal, the only maximal ideal. This implies by hypothesis x belongs, 1 minus u is a unit, and hence 1 minus u is a unit. This implies r x is a unit. This implies x is a unit. That is a contradiction. To the assumption that x is not a unit. X is a non-unit. This implies x belongs to M, and that implies M is a set of all non-units. That implies M is the unique maximal ideal. Is this clear? So, if 1 plus for any maximal ideal 1 plus x is a unit for every x in the maximal ideal will imply that it is a local ring. Okay, ring is local and M is the unique maximal ideal. So, we had been talking about unit collection of units. Now, there is a subcollection, right. We have seen that any not units, we were talking about non-units. Now, a subcollection of non-units, interesting subcollection are set of all zero divisors and set of all nilpotents. Right. So, first let us collect all the nilpotents. So, set of all x is a nilpotent. We saw that collection of all non-units do not necessarily form an ideal. What about this collection? What is the definition of nilpotent? There exists a power n such that x power n is 0. Now, will this form an ideal? This is certainly a proper subset of A, right, because none of the units, in particular 1, cannot be in n. Therefore, this is indeed a proper subset. Is this an ideal? For example, if I take, if x comma y belong to n, can we say that x plus y belong to n, or what does this mean? Then there exists n m such that x power n is 0 and y power m is 0. The question is, can we say x plus y is nilpotent? if I take, this implies x plus y whole power n plus m, this will, so in the binomial expansion any of the monomial term will contain either a power of x power n or a power of y power m. So therefore this has to be 0. This implies x plus y belongs to n. And what about, so what are the other conditions? Associativity, if x belongs to n, can we say minus x belongs to n? Straightforward, right? The same power will work, right? Yes?
You take n plus n minus 1.
Huh? Sorry?
N plus n minus 1.
Will it go through? There will be a power, yeah, minus 1 might also go through. I mean, see, you don't really have to worry about what power, right? Asymptotically it is 0. Some high power is 0, that is all you have to worry about. So if I take, if x belongs to n, then minus x belongs to n, that is pretty straightforward. What about if x belongs to n and r belongs to a, then is r x in n? Again the same power, the x, if x power n is 0, then r x whole power n will be 0 again. So therefore x power n is 0 will imply r x power n is 0. This implies r x is also nilpotent. So what we have shown now is that the set of all nilpotent elements form an ideal, form a proper ideal of this is what we proved. Now there is an interesting thing to observe here. There is an interesting thing to observe here is that if I take a nilpotent element x in n, then x power n is 0 by definition, right? But then 0 is an element that belongs to all ideals. So this, for any element in the n, some power belongs to all ideals. In particular, if I take a prime ideal, what does this say? 0 belongs to prime ideal, any ideal it belongs to. So if you, in particular, if I take a prime ideal, x power n belongs to the any prime ideal. What does that imply? X belongs to p, or x power n minus 1 belongs to p. Now you can keep coming down. X belongs to p. So this says that the nilpotent elements, all the nilpotent elements are in all the prime ideals, right? If p is a prime ideal of A, suppose P is a prime ideal of A. If x belongs to n, then x power n is 0, which belongs to P for some n, and P being prime, this implies that x belongs to P. Or in other words, what we have shown here now is that this n is contained in intersection of all every element of n is contained in all ideals, all prime ideals, or in other words, this is contained in the intersection. So, there is a natural question whenever you see an inclusion, naturally one tends to ask whether this is a proper inequality or actually an equality. So, the question is, are they equal? So, let us try. Suppose, so I want to show that every element here is here, or in other words, if I show that if x is not here, then it cannot be here. Now, how do I show that it cannot be here? It is not in the intersection. If I want to show that it is not in the intersection, yeah, I have to produce a prime ideal which avoids that element. Okay? So, let us start with an element which is not in n. This implies x power n is not equal to 0 for every n bigger than or equal to 1. I want to get a prime ideal which avoids x. Okay. So, again this is, as I mentioned earlier, we apply the Zorn's lemma tool in this case. So, let us look at this collection of all proper ideals of I, an ideal such that x power n is not in I for every n. I just look at all the ideals which do not contain any power of x. Is this non-empty? The 0 ideal, right? X power n is non-zero for every n, which means 0 ideal is in this one. The ideal 0 belongs to sigma. This implies sigma is non-empty. Now, how do you show and how do you proceed? Take a chain of ideals, be a chain in sigma. What is the natural upper bound that you can think of? Union. Let I be equal to union In, n from 1 to infinity, then I is a proper ideal. So, I will leave that as an exercise to verify for yourself. Now, the question is whether I belongs to sigma. What is meant by I is not in sigma? There exists some power of x in I, but if an element belongs to I, it has to be in one of the INs. That again contradicts. So, therefore, and I belongs to sigma. So, I will just write it as verify. But then So what this is an upper bound for this chain. So this I is an upper bound for the chain. So by Zorn's lemma, sigma has a maximal element. Let me call this maximal element P. P be a maximal element. I claim that this is a prime ideal. Okay. So let AB belongs to P. If A is not in P and B is not in P, we want to show that either A belongs to P or B belongs to P. Suppose both are not in P, that would imply that P plus A is not in sigma and P plus B is not in sigma, right, because both are strictly bigger ideals. This will imply that a power of x belongs to this ideal and a power of x belongs to this ideal. This implies there exists n with n and m with x power n belongs to P plus A and x power m belongs to P plus B. So I can write x power n as some z1 plus r1a and x power m as z2 plus r2b. Now if I take their product, what do I get? X power n plus m will be z1 z2 plus z1 r2b plus z2 r1b plus r1 r2 ab. Now what can you say about this product? What can you say about AB? AB is in P, Z2 is in P, therefore this is in P, this is in P, this is in P. The whole thing is in P. That is a contradiction. So therefore P is a prime ideal and P does not contain any power of x, in particular x is not in P. So we have obtained a prime ideal that avoids x. If x is not nilpotent, there exists a prime ideal that avoids x. Okay. So what we have proved now is that n is indeed the intersection of all prime ideals. Stop here.